With a new chapter, alkenes. Is this clear? So obviously we start with this point. What are alkenes? Alkenes are aliphatic unsaturated hydrocarbon. Aliphatic unsaturated hydrocarbon, okay, which has at least one aliphatic, which has in its structure at least one carbon-carbon double bond, as one carbon-carbon double bond. Is this clear? So those having two double bonds before that, so their general formula is CnH2n, because for each pi bond that is formed, which becomes a multiple bond, two hydrogens are removed actually. So that is how we get CnH2n plus 2 was that of alkane. So CnH2n will be that of alkene. If more than one double bond, if more than one double bond is present, then it is called as alkadiene and alkatriene, and so on and so forth. Is this clear? Now we directly come to what? We come to the nomenclature of alkene. So we talk of nomenclature of, we will talk of isomerism in alkene and then nomenclature. So we straight away talk about isomerism in alkene. So we have structural isomerism and geometrical isomerism. Is this clear? So we talk of structural isomerism. When we talk of structural isomerism, what happens is we have straight chain and branch chain. So for example, you have CH3, CH, double bond CH, CH3. So this is butene, and you have CH3, double bond CH2, CH3. This is isobutylene. This is isobutylene. We can have in structural isomerism also positional isomerism. So what is positional isomerism? Molecular formula is same. So molecular formula is same. Molecular formula is same, but position of the double bond, differs. The best example of this is you have one butene CH2 double bond CH, CH2 CH3. This is but1-ene, and you have CH3 CH double bond CH, CH3. This is but2-ene. This is but2-ene. So you have but1-ene and we have but2-ene. It is clear. Then we also have functional isomer. Functional isomerism. So alkenes, cycloalkane. Cycloalkane. So what are functional isomers? Molecular formula is same. Molecular formula is same, but functional group is different. But functional group is different. Molecular formula is same, but functional group is different. So we would have over here cycloalkane and alkene. So cyclobutane is an isomer of butene, CH2 double bond CH, CH2 CH3. This is but1-ene or but2-ene. So you can see cycloalkane is functional isomer. Then we come to geometrical isomerism. So geometrical isomerism is what? It's an isomerism. So you have a double bond. So across the double bond, when the same, what do you call, groups are arranged on the same side, then this is called as cis isomer. When the same groups are, what do you call, placed on the opposite side, or when similar groups are placed on opposite side, then this is called as trans isomer. So this is what is the explanation. Now we can understand the definition. The isomerism which is due to difference in the spatial arrangement of atoms or groups across the double bond. So across the double bonds in the space, if similar groups are on same side, cis isomer, similar groups on opposite sides called as trans isomer. As a thumb rule, trans isomer is more stable than cis isomer because it is having a less dipole moment. Sometimes it has a trans isomer has a dipole moment of 0. So it will be more stable. Is this clear? So between cis 2-butene and trans 2-butene. So this is an example of what? This is cis 2-butene and this is trans 2-butene. Trans 2-butene is more stable than cis 2-butene. Is this point clear? So when you come to nomenclature, there are two types of system. One is the common system or the common name, and then we have the IUPAC system of nomenclature. See, in the common system, what happens is the name of the alkene is obtained by changing the suffix ane. So ethane ending ane is replaced by the word ylene. So ethane, the corresponding alkene would become ethylene. Ethane is the alkane, remove 2 hydrogen from that, the corresponding alkene would become ylene, ethylene. And the position of the double bond is indicated by Greek letters alpha, beta, gamma, etc. So the first member of the homologous series is obviously CH2 double bond CH2. CH2 double bond CH2 in the common system. In the common system is called as ethylene. Whereas in the IUPAC system, we have root name. So how many carbon atom does it have? 2. So root name is 8th and primary suffix is ENE. So because it has a double bond, primary suffix is ENE. Then we have CH3, CH double bond CH2. So this 3 carbon atom is propane. Propane ka ending E is ANE is replaced by YLENE. YLENE. So it becomes propylene. Whereas it becomes over here 3 carbon atom, root name is prop, primary suffix is ENE. So it becomes propene. Then we come to the third member. We have positional isomers. So this would be CH2 double bond CH, CH2 CH3, and the fourth one will be CH3 CH double bond CH CH3. So this will be called as, so since on the first carbon atom, the double bond is on first carbon atom, this will be called as alpha butylene. Whereas in IUPAC system it will become but 1-ene. This is beta butylene, whereas in the IUPAC system we will call this as but 2-ene. Okay. Then the fifth one we can have is a very this thing, what do you call, alene. So if you have alternating double bond CH2 CH CH double bond CH2, this compound is called as alene. Whereas in the IUPAC system it will be called as buta 1,2-diene. Buta 1,2-diene. Okay. I am not dwelling too much into the nomenclature because this is how it follows. Is this point clear? We would rather come down to, whereas in the IUPAC system, there is one last point, if the double bonds are equidistant. Now, sixth one is a very important point which we should note. If the double bond is equidistant, if the double bond is equidistant from two ends, number the carbon atoms from that end which is nearest to the first branching, which is nearest to the first branching. From that end which is nearest to the first branching. So if you have finished this, then what happens is we will start with understanding what are the radicals of alkene. So what is a radical? When you go on systematically removing hydrogen from the alkene, when you remove one, that will be a radical. When you remove two, that will be another radical, so on and so forth. So when you remove one hydrogen, what is the name of radicals which are formed? Is this clear? So if I have ethene, CH2 double bond CH2, this is ethene. If I remove one hydrogen from that, the radical I get is CH2 double bond CH. This radical is called as vinyl. So polyvinyl acetate, PVA, polyvinyl chloride, PVC, polyvinyl chloride. Is it clear? So vinyl. So when you remove one hydrogen from ethylene or ethene, the radical formed is called as vinyl. Now let us look at propene. CH3, CH double bond CH2. There are three possibilities. When I remove this hydrogen, then I get CH3, CH double bond CH. This is called as the 1-propenyl. Then if I remove this hydrogen, then the radical is called as CH3 double bond CH2. Then this radical is called as 2-propenyl. Very interesting one is, if I remove this hydrogen, alpha hydrogen, because this is the functional group, carbon atom adjacent to that is called as alpha carbon atom. So when I remove the alpha carbon atom, we will have the radical CH2, CH double bond CH2. This is called as allyl. So this was alene and this is allyl. So allyl is very important because this allyl hydrogen has a different kind of reaction. It is clear. So remember with propene, so this was propene. Propene gives you three radical, 1-propenyl, 2-propenyl and allyl. We are talking about methods of preparation of alkene. When we are talking of methods of preparation of alkene, the first method of preparation of alkene is by elimination reaction. So elimination reaction has two aspects. It's also called as beta elimination. You can eliminate from alcohol. What can you eliminate from alcohol? You can eliminate one H and one OH. Is this clear? So then that reaction is called as dehydration. Then that reaction is called as dehydration. Or you have an alkyl halide. So in case of an alkyl halide, what happens is, you remove a halogen and the adjacent hydrogen. That's why it's called beta elimination. Why? Because the halogen, the carbon containing halogen is called as alpha carbon atom. The carbon atom adjacent to that is called as beta carbon, and the hydrogen on that is called as beta hydrogen. So this is also called as dehydrohalogenation. Dehydrohalogenation. Is this clear? So the first thing we are talking about is dehydration of alcohol. Dehydration of alcohol. So what happens is, what is the dehydrating agent? The dehydrating agent mainly we use is concentrated sulfuric acid, or you can use alumina, Al2O3. They are strong dehydrating agents. So what happens with concentrated sulfuric acid is, you have suppose ethyl alcohol, CH3, CH2, OH. So I told you that the carbon containing the OH group is alpha carbon, the carbon adjacent to that is beta. So OH group is eliminated along with the hydrogen, and so what happens? So this is nearly at, so we use concentrated sulfuric acid at around 170 degrees centigrade, 441 Kelvin. Okay, but as I am an old timer, I am always used to remembering things in degrees centigrade. So this is how I have taught. So Kelvin, just add 273. So what happens is, you get CH2, you get CH2 double bond CH2 plus H2. Okay, so first is, what is the kind of question that they can ask in this? First is the decreasing order. I mean, what kind of what do you call question they can ask is ease of dehydration. Ease of this is the this is a question for NEET JEE. Ease of dehydration. So when you talk of ease of dehydration, tertiary alcohol gets easily dehydrated as compared to secondary, as compared to primary. Is this point clear? And that is reflected in the concentration of sulfuric acid and temperature. So if it is secondary alcohol, it will really be 60%, 100 degrees. If it is tertiary alcohol, it is nearly 20% at 90 degrees still. So the concentration of sulfuric acid even being less, tertiary will undergo dehydration. Is this point clear? We come to a very interesting aspect called as Sadziev rule. Now what happens is, listen carefully. We have, suppose if I take sec-butyl alcohol. See, I'll write the reaction, explain the mechanism, and then we will write the rule. So we have CH3, CHOH, CH2, CH3. Okay. So this is sec-butyl alcohol. Now sec-butyl alcohol, when you treat with concentrated sulfuric acid, okay, I'm just writing the temperature. Temperature we know is around 100 degrees centigrade. So what happens is it forms two different products. So you get CH2 double bond CH, CH2 CH3. This is but1-ene, and you get CH3 CH double bond CH, CH3. This is but2-ene. So we find that but1-ene is 20% and but2-ene is 80%. Even in that, to be going very deep into 2-butene, from the entrance exam point of view, you get cis-butene, cis-2-butene. So you have CH, CH3, double bond. So you will get cis-2-butene and trans-2-butene. This is trans-2-butene. That is a major product. So not it's 80%. Even in that 80%, the major product will be trans-2-butene, because trans-2-butene dipole moment is equal to 0. Dipole moment equal to 0. So it is more stable. So that is formed. So from this arises what we call as Sadziev rule. Is it clear? So what is Sadziev rule? Is it clear? The Sadziev rule says that, I will just remove the first part and then write Sadziev rule over there. So what does Sadziev rule say? Sadziev rule says that see, according to Sadziev rule, what happens? We know that in dehydration of alcohol, OH has to go necessarily. So what happens in case of 2-butene is, you can see over here, if it goes with this hydrogen, this carbon was primary. If it eliminates with this, this was secondary. So when it eliminated with the least substituted hydrogen, this was a hydrogen attached to a secondary carbon atom. So then what happens is you got a larger product. And this is exactly what Sadziev rule says. What does it say? It says that when there is a possibility of formation of two different alkene, that alkene is formed in large excess. That alkene is formed in large excess in which hydrogen atom is eliminated, from the more substituted carbon. So once again I'll try to explain. You have a OH group, you have adjacent hydrogen attached to a primary carbon atom, and this adjacent, both are beta, attached to a secondary carbon atom. So OH would prefer to go with that. Imagine another scenario, you have OH group, this is attached to a secondary and this is attached to a tertiary, hydrogen attached to a tertiary carbon atom. Then this alkene would be preferably formed where OH gets eliminated with the hydrogen attached to a tertiary carbon atom. So this is what is Sartziev rule. Is this clear? Now what happens is, why is it so? So this can be explained with the help of mechanism. So we cover both Sartziev rule as well as mechanism of dehydration. So what happens over here is, listen carefully, then eliminate from more substituted carbon. So mechanism. So we take sec butyl alcohol. So we have CH3, CH, OH, CH2, CH3. Okay. Now sulfuric acid we know dissociates to form H plus plus OSO3H minus. So step 1, so this itself is a question on its own. Step 1 of the mechanism is what? It is protonation. So this was asked in one of the exam. The step 1 of dehydration of alcohol is, it's a multi-step reaction. Na? Step 1 is protonation, addition of proton. So when you add a proton, H plus, see over here this oxygen has got a lone pair of electron. So this is going to attack over here. So what do you get? You get CH3, CHOH, H plus, and then you get CH2, and then you get CH3. See, I had always told you, moment electronegative element acquires a positive charge, it's going to be unstable. So here what happens, look at how I am putting the this oxygen goes with the bond pair electron of carbon also. Are you understanding? It becomes H2. Oh, its lone pair is restored. But in the bargain, what do you get? You get CH3, CH plus, CH2, CH3. Okay. So this is the second question. So what is the first MCQ that we could possibly look for? that the first step in the dehydration of alcohol is protonation. What is the second step? The second step, when it says formation of intermediate. The intermediate formed is a carbonium ion. Is a carbonium ion. Okay. Now just imagine we have OSO3H minus still left out. Now it is going to remove this hydrogen or this hydrogen. So we get two possibilities. So you have one possibility is, so this hydrogen has gone. So this carbon is negatively charged. Then what do we have? We have CH. Then this carbon has gone, so it is plus. And then what do we have? We have CH2, CH3. This is one possibility. What is the other possibility? You have CH3. This carbon was positively charged. The adjacent hydrogen goes away to form sulfuric acid. So you have CH. You have a minus charge over here. Okay. And then you have CH3. Okay. Now what happens is, listen carefully. I told you always that molecule which has more number of covalent bonds and no charge is more stable. So here both have charges, so both are unstable. In order to achieve stability, what are they going to do? The carb anion, which is electron rich, is going to give electron to carbonium ion and form a pi bond. So that means stability of carb anion is involved. So that is a question on its own. So when I put like this, understand, sometimes there is no space to write JE neat means I mean. So stability of carb anion is, stability of carb anion is primary greater than secondary greater than tertiary. So obviously what do you get? This carb anion is more stable and this carb anion is less stable. So because it is less stable, what is it going to do? It's going to lose its electron. So every time, it's not the stability which is taken into consideration. Sometimes it's the instability of a molecule which could result in formation of a certain product. And the example of that is over here. The secondary carb anion is more unstable, so it loses electron much more easily and restores the pi bond, and therefore you get 2-butene as a major product. So that gives rise to CH3, CH double bond CH, CH3. That is butene. That is butene. Understand what I am saying? Butene. Is this point clear? Second method of preparation will be from alcohol will be dehydration using alumina. Dehydration using alumina, that is Al2O3. So suppose I'll take the simplest reaction, CH3CH2OH. Again it's a beta elimination. So what happens is when I treat with alumina, Al2O3 at around 623 Kelvin. See here, try to understand that this is a temperature dependent reaction. Because if the temperature becomes slightly low, it could happen that a large amount of ether will be formed. So that's why mentioning temperature over here is very important. You get CH2 double bond CH2 plus H2. Okay, so this was dehydration using alumina. We'll now come to dehydro. Method of preparation is, again it's an elimination reaction. This is clear. So that is by dehydrohalogenation. By dehydrohalogenation, by dehydrohalogenation of alkyl halide. So this will be dehydrohalogenation of alkyl halide. So we have, let us take the example of, simplest example, we take ethyl bromide. Okay, we'll come to the NEET question first. So NEET JEE, what can be the question that they can ask? Hydrohalogenation, which would be easily had. So it will be alkyl iodide, that is iodide greater than alkyl iodide greater than alkyl bromide, greater than alkyl chloride. Then the second thing is, for the same isomer, for isomeric alkyl halide. So this is A, this is B. Two questions are possible. For isomeric alkyl halide, then it will be tertiary alkyl halide greater than secondary, greater than primary. So these are two MCQs possible in this. We'll come across much more in the course of our study. Is this point clear? See, I always believe that you pick up all these skills while you are learning the this thing topic. You do not sit separately with the MCQ book and then try to look at the summary and then try to answer. This is duplication of work. You pick up all the skills while you are doing it and then just straight away start with the MCQs. A 10% MCQs may be more than concepts, may be more. That can be caught up. But doing the same thing repeatedly has no meaning. So now what happens is, let us take, we have CH3, CH2, Br. Now this, when you react with alcoholic KOH, is very important. This alcohol as a solvent is very, very important. Alcoholic KOH, and when you heat it, again you can see over here that this will be an example of beta elimination. Why? Because this is the carbon atom containing the halogen, so this is beta. Alpha carbon, this is beta carbon, so beta hydrogen is eliminated. So you will get CH2, double bond CH2 plus HBr. But that HBr is a halo acid, it is going to react with KOH. So you will get KBr plus H2O, KBr plus H2O. So this is ethyl bromide. So once again we have over here, what do you have? Sargieff rule. So what can we say? If I take sec butyl bromide, CH3, CHBr, then we have CH2, CH3. So this is sec butyl bromide. When I react with alcoholic KOH, what happens is we get two possibilities. So because over here, again you can see carbon containing the halogen is alpha. So this is also a beta hydrogen and this is also a beta hydrogen. So what does Sargieff's rule say? Hydrogen will be preferentially eliminated from that carbon having attached to a more substituted carbon. Is this clear? So it will be preferably eliminated from secondary or tertiary when there is a possibility. So we will have again over here CH2 double bond CH, CH2 CH3. This is but1ene, and we have CH3 CH double bond CH, CH3. This is but2ene. So again this will be 20% and this will be 80%. Are you understanding? So this is Sargieff rule once again over here. Is this clear? The mechanism of dehydrohalogenation. Mechanism of dehydrohalogenation. See, this is called as E mechanism because elimination, this is called as E. And you have, in case of what you call primary and secondary alkyl halide, you will have E2 mechanism. So in case of primary and secondary alkyl halide, so this is our material for JEE NEET. Okay, primary and secondary alkyl halide, they proceed by E2 mechanism. Okay, whereas with tertiary alkyl halide, okay, it will be E1 mechanism. So let me discuss this. Now what happens is, if you have an alkyl halide, so you have CH3, okay, CH2Br plus OH minus. So step 1, what happens is that there is a slow step where the bromine goes out as bromide. So this is the slow step. So in the slow step, what happens is you have CH3, CH2 plus Br minus. Then what happens immediately? So again over here what happens? This will be a carbonium ion intermediate. Carbonium ion intermediate. Now what happens is this carbonium ion intermediate the base OH minus immediately removes this H plus. So this is a very fast step, quick step. So what happens in this fast step is you are now left with a carb anion and you are left with a carbonium ion. I told you the electron rich will donate to the electron poor to restore the double bond. So therefore we get CH2 double bond CH2, that is ethene. Are you understanding? So this is the mechanism of dehydrohalogenation. So remember these two. If it is primary and secondary alkyl, it is E2, where the concentration will depend on both. When it is E1, it is only dependent on the concentration of the alkyl halide. That is the meaning of that. So when you do chemical kinetics chapter in your physical chemistry, you will understand this better. At the moment, just understand the point that's E1, E2, carbonium ion is the stable intermediate. Is this point clear? Then the next one we come is dehalogenation reaction. Okay. Halogenation of vicinal dihalide. So let us first try to understand, because this is the formative stage that you have. We'll try to understand what is a vicinal dihalide. See, when one hydrogen, so you have an alkene, okay. So when one hydrogen atom of an alkane, when one hydrogen atom of an alkane is substituted by, when one hydrogen atom of an alkane is substituted by a halogen atom, then it is called as alkyl halide or alkyl halide, or it is also called as monohalogen derivative. So Rx is the general formula. So the monohalogen. Now the question arises, if there are two hydrogen to be removed, okay. So when two hydrogen are removed, then they are called as dihalogen derivative. So when you now talk about dihalogen derivative, the question comes is, where have you removed the hydrogen from? If you have removed both the hydrogen from the same carbon atom, so then this is called as geminal dihalide. So what is a geminal dihalide? Both the halogen, both the halogen atom, both the hydrogen, okay, both the hydrogen atom substituted by halogen is on the same carbon atom. On the same carbon atom. This is clear. So generally we name them as alkylidene dihalide. For example, we have CH3, CHCl. So this will be called as ethylidene dichloride. Now the other one is when the hydrogen atoms substitute are adjacent to each other, they are called as vicinal dihalide. So what happens in case of vicinal dihalide is adjacent hydrogen atom are substituted by halogen atom. So adjacent hydrogen atoms are substituted by halogen atom. So the general name would be alkaline dihalide. Let us look at a case like this. So we have CH2Cl. So this is ethylene dichloride. Okay. So this is vicinal. So here our heading is dehalogenation. The word de means removal of halogen from a vicinal dihalide. So what would be the dehalogenating agent? It will be simply zinc and alcohol. So what are we going to have? So if I take CH2Br, so this is ethylene dibromide, react this with zinc in presence of alcohol, okay, heat it. So what are we going to have? We are going to have CH2 double bond CH2, that is ethene plus ZnBr2, zinc bromide. So this is about dehalogenation of vicinal preparation. The fourth method of preparation is by hydrogenation, by reduction or hydrogenation. See, partial reduction of alkyne is done in presence of or using catalyst palladium, calcium carbonate and lead acetate. See, here there is a pertinent question about lead acetate. It is clear. Or the alternative we can use is palladium barium sulfate, and I think we can use quinoline also in this, where we can have, or we can use palladium barium sulfate with quinoline. See, the role of lead acetate and quinoline, they both act as catalytic poison. I'll write it separately because that's a very important point which has been asked. Rosenmund reduction, next year you will come across. So lead acetate and quinoline, okay, acts as catalytic poison. So when they act as catalytic poison, they allow further reduction to form an alkane. Is this point clear? So this is also called as Lindlar catalyst. It is called as Lindlar catalyst. See what happens is, suppose you have, let us say, CH3, C triple bond CH3. So you got hydrogen, source of hydrogen, you used palladium, calcium carbonate and lead acetate. So with Lindlar catalyst, you will always get, in this case, cis but 2-ene. So what I'm trying to tell is, with Lindlar catalyst, you will always get a cis isomer. What if you want a trans isomer? Then you change the reducing agent. Okay. So in order to get trans isomer, we use, let's take the same example. We have but2-ine. So this is but2-yne. But here you will use liquid ammonia and sodium. So that should create a trans isomer. So liquid ammonia and sodium itself will be nascent hydrogen. So what will it give? It will give CH3H double bond HCH3. So this will give trans but2-ene. Are you understanding? So this reduction itself, I would say, is a very important topic, because a lot of time they ask these questions on which is cis isomer, which will form trans isomer, so on and so forth. It is clear. So it's basically an addition reaction or addition of hydrogen. So addition of hydrogen is nothing but reduction. Alkenes. Physical properties of alkene. The first one is, physical means it was solid, liquid, gas. So C2 to C4 are gases. C2 to C4, they are gases. Then we have C5 to C15. C5 to C15 are liquids, and greater than C16 they are solids. Insoluble in water, insoluble in water. The third point is that for isomeric alkene, this is I have taken from some question from some MCQ and mentioned it over here. You will suddenly wonder, instead of talking about boiling point, melting point, suddenly why is he coming to isomeric alkene? Because this was a question in some MCQ in some exam. So I have taken it over here. So we have, for isomeric alkene, what can you say as branching increases? As branching increases, okay, boiling point decreases. So as branching increases, boiling point decreases. As branching increases, boiling point decreases. See, we talk about dipole moment. For symmetrical and trans alkene A, for symmetrical and trans alkene, okay, dipole moment nu is equal to 0. Is this clear? Whereas B, obviously when dipole moment is 0 means stability increases. There is a direct connection. Unsymmetrical and cis alkene possess certain dipole moment. Unsymmetrical and cis alkene possess dipole moment. Possess dipole moment. Then we come to what stability. Fifth point. Again, this stability concept I brought in here because this question has been asked in a certain entrance exam. Okay, so you might not find it in your textbook or something like that. Is because of this. I am taking up questions also and trying to solve it over here. So when we talk of stability of alkene, what do we have when we talk of stability of alkene? Greater is the number of alkyl groups attached to the double bond. So we have greater is the number of alkyl group, greater is the number of alkyl groups attached to, greater is the number of alkyl group attached to the double bond carbon atom, more stable is the alkene. More stable is alkene. So we would have, look at this, its stability will be greater than it will be greater than and this will be greater than So now we look at the chemical properties.